Assalamualaikum and good morning, everyone.
Good morning, sir.
Okay, so today we are going to continue with lecture 5A that we stopped last week. So I think we have covered until this ideal integral compensator. So if I didn't cover this one, please let me know. Okay, so we will continue with an example of lag compensator. Okay, so we have learned is a easier to build version of integral compensator. Okay, if you are going to build this using an electronic component. So the purpose of lag compensator is to reduce the steady state error while maintaining similar transient response. So the purpose here is to reduce steady state error. So that's the purpose of lag compensator. So let's say if your system has an error, let's say 40%. So you want to reduce the error maybe until 5%. So you can use integral or lag compensator. But when reducing the steady state error, you want to maintain similar transient response such as percentage overshoot, settling time, and so on. So this can be done by adding a compensator poles and zeros such that the value of compensator 0 must be less than compensator pole. So if you look at this figure here, ZC is located more to the left compared to PC, meaning that ZC is less than PC. So if you are going to
Tak nampak dah, doktor.
Sir, sorry. Sir dah share screen ke, sir?
rasa macam dah share. Nampak tak?
Baru ada, baru ada.
Okay. Okay, so if you look here, ZC is less than PC. So if you are going to build a lag compensator, you must remember to add ZC that has value more negative than PC. So the first figure here is the figure of the root locus when you don't have the compensator. And this point P here is the point that when you plot the time response later, maybe in MATLAB, you will get the time response following certain criteria. So you want to maintain the same point P, but you want the point, the time response at point P to have a smaller steady state error. So what you are going to do is you add a ZC and PC such that the root locus, the new root locus will also cross this point P here. So when it crosses this point P, the time response will be the same, the transient response, but the steady state error will be changed slightly according to the value of ZC and PC that you add later. So the ZC and PC, when you add, it will introduce a new angle here. The angle of that measures from this pole N0 to this point P. And these two angles, when you add it such a way that the angle and length can be cancelled out. Okay, we will see later what this means. Okay, so let's look at an example. Before the example, let's look at how much you can reduce the error, the steady state error, when you add the compensator. So when you add a compensator here to this type 1 system, so this is type 1 because it's S power of 1. So when you add this compensator, then for type 1, you have KV. So you calculate KV using the limit theorem, and then you end up with this formula here. So the original KV or KV for the system without compensator is just this K times Z1, Z2, and so on over P1 times P2 and so on without ZC and PC. But for the system, for KV, for the new system with compensator, you have ZC type over PC. So the relationship for the KV new is equals KV original, or the KV for system without compensator times ZC over PC. So if you use the formula to get the error, which is 1 over KV, so you get error for the new system equals error for the original system times PC over ZC. So it just reverse PC over ZC, just inverse. So now you know that the error is reduced by this ratio PC over ZC. So let's say if you want to reduce by 10%, let's say if you have original error 40%, and you want to reduce it to, let's say, 5%. So this is 8 times reduction. So the ratio must be 1 over 8. Okay, you reduce this by 1 over 8. Okay, so you know the ratio from the specification given. So you can determine PC and ZC by using the amount of error reduced. Okay. So let's take a look at an example. So let's say you are given this system with gain K and plan 1 over S plus 1 times S plus 2 times S plus 10. So design lag compensator to improve the steady state error of the system by 10 times. So here, what does this mean is that the original error is reduced by 10 times. So you get the new error. So you want the new error reduced by 10 times from the original error. So you are given the transient response damping ratio equals 0.174 at dominant poles, this one. Okay. So this example is actually similar to example in ideal compensator that I've shown last week. Okay. Similar example, but different kind of compensator. So from this example, I have calculated this value, the gain K at this point here. Or the damping ratio is 0.174. And then this is the point of intersection between the line and the root locus. Okay, the root locus is the root locus of this system. So if this question come out in exam, usually we will give you this value, dominant pole, and also this gain K value, because to calculate this value, actually the calculation is quite tedious. Okay, but for your project, you can determine this from MATLAB. Okay, you can just plot the root locus and then plot this line here and then determine from MATLAB this intersection point where is the what is the dominant pole and also what is the gain k. But if come out in exam, we will give you these values because to determine the intersection is very hard. So you are given this and you can calculate the steady state error using the formula that we have learned in lecture 4D, 4B, sorry. So this value has been calculated from previous example. So similar calculation here applies to this to the second example. So this is the error of original system. And then this is the KP of original system. So why KP? Because the system is of type 0. So for type 0 system, you have steady state error when you apply a unit step input or when you have KP. But if you have KV and KA, then you don't have error. So you want to reduce times. So the new error will be 0.0108. And then we calculate the new KP using this formula. So we get the new KP equals 91.59. So we get the new KP. Now we need to determine what is the value of PC and ZC so that we can plot the new root locus. So using the formula E new equals PC over ZC E ori, or you can use the formula KP. It will produce the same answer. Okay. So the ratio for ZC over PC will be 11.13. So you know that the ratio of ZC over PC is 11.13. So we need to choose a suitable value of PC and ZC. So in this example, because we want to develop a lag compensator, and we must use ZC less than PC for lag compensator. So you choose a value for PC first. So usually we choose PC that is close to 0. So in this example, it chooses PC equals 0.01. So when you choose PC 0.01, then you can calculate ZC from the ratio. Okay, from this. So you get ZC about 0.111. And then we can, if you use MATLAB, you can plot these values on the root locus. And then the root locus will, a new root locus will be generated for you automatically in where you don't have MATLAB. Usually you are required to determine PC and ZC and then the final K value, which I will show you in the next compensator later. Okay, so this is the comparison between system with uncompensated and with compensator. So the difference is that the system with compensator has a new poles and zero, and the steady state error is reduced here in the lag compensated system. So later I will show you an example how to use MATLAB for some of the tutorial question. Okay. Okay, now we move on to the second type of compensator, which is the derivative compensator. So previous example is about integral compensator and lag compensator. So now it's the second type of compensator, which is the derivative compensator. So the purpose of derivative compensator is to reduce the settling time while maintaining the same overshoot and also the same steady state error. So let's say you are given this transfer function or system, and you have the specification to have percent overshoot 16%, and you want to reduce the settling time by 3 times, meaning that the settling time ORI, you want to reduce it by 1/3 or 3 times. So firstly, what you need to do is you need to calculate the transient response performance parameters. So you are given 16% overshoot. So you can calculate damping the formula from the second order system. Okay, so using this formula with 16% overshoot, then you get damping ratio equals 0.504. Then if you use MATLAB and plot this root locus, the transfer function into root locus, then you can determine the settling time and also the omega n. But I will show you later how to determine this in MATLAB. So this is the TS for the original TS. So after you determine the original TS, then you can determine the steady state error. So firstly, you can determine the static error constant and then the steady state error. So this value is determined from MATLAB. Okay. So you get two things here. First is the damping ratio for 16% overshoot. And then you get the TS for original system without compensator. So you want to reduce the settling time by 3 times. So just reduce by 3 times, you get 1.117. And then you can determine the new damping ratio times omega n equals 3.582. So this is determined by this formula here. So TS equals 4 over omega, damping ratio times omega n equals 1.17. So you get TS equals, omega n, damping ratio times omega n equals 3.582. So from this value, the damping ratio times omega n, you can determine the omega n value by assuming you maintain the system, the new compensated system, with 16% overshoot, meaning that you maintain the damping ratio. So always remember, damping ratio and percent overshoot are related to each other. So if you want to maintain percent overshoot 16%, meaning that you maintain the damping ratio, the same damping ratio. In this case, it's 0.504. So to maintain 0.504, meaning that you change the value of omega n. So the new omega n is 7.11. So you can determine the new poles for the new system or the new dominant poles using the formula here. So this formula is actually in the first a few slides of this lecture. Okay, you can refer that later. So to get the real part of the new pole is just using this formula here, and to get the imaginary part, just use this formula. Okay, so it's all about substituting the formula with the values to get the answer. Okay, so cuma kena tahu formula apa nak pakai, tu je. So however, when you determine the new poles, you will see that the new poles are not on the original root locus. So you need to design a compensator so that the root locus will change in shape and then crosses the new poles. So how to determine that? You need to So in order for the new poles to be on the root locus, so the sum of angles must equal 180 degree. So when you add the new PC and ZC here, you have to calculate the angle of each of the poles and 0 to the point of interest. And then make sure that the angle, when you sum, you get 180 degree. So in this example, the example only add one ZC. So you get the angle θ1 is from this pole here, θ2 and θ3 from the other poles. So we don't know what is the angle for ZC because we don't know what ZC yet. So we need to determine the location of ZC. So to determine the location of ZC, we need to determine the angle of ZC. So in this case, we determine the angle θ1, θ2, and θ3. And then plus ZC equals 180 degree. And then the baki, the remaining value is θZ or θZC equals 94.87. So the angle here is 94.87. So we need to determine this location here, this length A, assuming that this height we know already, which is 6.144J. So to determine that, we need to use tangent. So in this example, the example use tangent, or you can rewrite slowly so that you can you know what is the value of A. So we know that θZ is 94.87. So 180 minus 94.87 equals this angle, which is tangent minus 1, 61.4 over A. So to get A is to use this calculation. So A is about 0.523. So the position here is 0.523. Oh no, the position here, sorry. So the length here will be 3.582 minus 0.523, which is 3.06. So the compensator is this one. Okay, it's okay if you're confused right now. Let's look at another example later. Okay, so we have seen the ideal derivative compensator. So to further to use a derivative compensator, it's better if we can develop a compensator that is easier to build, which is the lead compensator. So lead compensator is a type of derivative compensator, but an easier version to build. Okay, if you are going to use electronic system to build the compensator. So lead compensator generally used to speed up transmission response by improving the settling time and also percent overshoot, and improve the system stability by shifting the root locus to the right. So compared to lag compensator, so lag compensator is used to reduce steady state error, but for lead compensator, it is used to reduce the settling time. Okay, so for lead compensator, what you need to do is you add ZC bigger than PC. So for lag compensator, you add ZC less than PC. But for lead compensator, ZC bigger than PC. So the form of controller or the compensator is the same with lag compensator, but the procedure to determine ZC and PC is slightly different. So let's look at this example. So consider a plant with open loop poles 0, -4, and -6. Design a lead compensator that has 16% overshoot with threefold reduction in settling time. Given the dominant pole is -1.2 plus 2.06 J with a gain K 43.2. So in this example, it already plot for you the gain or the root locus of this transfer function. So here you get damping ratio and overshoot and frequency at this location here, at this pole. So we can list down the damping ratio is 0.503 and frequency is 2.38. So from these two values, you can determine the settling time of this original system. Okay, so this is the calculation to determine damping ratio from percent overshoot. So the percent overshoot given to you is 16%. Okay, so the damping ratio is 0.5039. And then we have the frequency, which is 2.38. So we can get the settling time equals, settling time equals this formula. 4 point over damping ratio times omega n. So if you are not given this information here, so you can determine the damping ratio from percent overshoot, and you can determine the frequency from this dominant pole here. So always remember the dominant pole 1.2 equals damping ratio times omega n, and then 2.06 equals this formula here. Okay, so in exam, you are given the percent overshoot and also the dominant pole. So you need to determine the damping ratio and also the frequency. After you determine the damping ratio and frequency, you can determine the settling time using the formula, this one. So the new system, you want to reduce the settling time by 3 times. So the new system, TS, will be 1/3 of this value here, which is 1.11. And then when you reduce the settling time by 3 times, then you need to determine the new dominant pole. So the settling time equals 4 over new damping ratio times omega n equals 1.11. So you get damping ratio times omega n equals 3.604. So you want to maintain the same percent overshoot, or you want to maintain the same damping ratio, meaning that damping ratio is 0.5039. So you calculate the new frequency, which is here, equals 7.152. And then you can determine the imaginary part of the new dominant pole. And then you get the new dominant pole, which is this value here. Okay, so we have determined the new dominant poles. Now we need to determine the location of PC and ZC for the compensator. So remember, for lead compensator, ZC must be bigger than PC. So usually you are given the value of PC or ZC, either one of them you are given. But if you are not given any of this value, PC or ZC, you have to use your own value. So in this example, the example gives PC equals -20. So ZC later will be have value bigger than this one. For example, -10, -5, etc. Okay. So you are given PC. So you need to determine ZC. So to determine ZC, we need to use the concept of angle. So the total angle will be 180 degree angle made from poles n0 to the new dominant pole. So firstly, you can plot all of the poles on an S-plane. So firstly, look at this transfer function. You have pole equals S equals 0, -4, and -6. So sketch them on the root locus. And then you have PC equals -20. So it's about here. And then the new dominant pole is this one. So you can roughly sketch on the root locus. So it should be here. And then you need to determine the angle made from each of the poles. Okay, so that's why you calculate the angle theta 1, theta 2, theta 3, and theta 4, which corresponds to this theta P1, theta P2, theta P3, and theta P4. And then total up the angle. So the total angle, angle of zeros minus angle of poles equals 180 degree. So you end up with ZC, theta ZC equals, the angle is 112.72. So if you have this angle, theta ZC equals 112.72, it should be located somewhere here. So it cannot located here, because if it is located here, then the angle will be less than 90 degree. So it should be located after this point negative 3.604, which is at this part here. So that the angle is more than 90 degree. So if I redraw this new graph, the new position of poles and zero, so ZC will be located somewhere here. So you need to determine this angle, which is this value 112.72, and then determine the length here, let's say A. So using the tangent formula, so 180 minus 112.72 equals tangent minus 1, 5.037 over A. So determine the value of A. Okay. So you get this value, negative 2.109. Okay, so when you get the value of ZC, then you can determine the new gain at this nominal pole using the length formula, which I will show you later. Okay, so that's it. I just want to tell you that if come out in exam, the question will be related to lag compensator. Okay, for lag compensator, it won't come out in final exam. Okay, so let me show you a little bit about your tutorial. Okay, so let's look at tutorial number 12. So there are many questions in this tutorial, so I will only show you example for question 1 and question number 3. And for question 2 and 4, you can try on your own. Okay. So for question 1, let's use MATLAB to determine the answer. Okay, so question 1 is about developing a lag compensator. Okay, so given a unity feedback system operating at 10% overshoot with transfer function below. So firstly, determine the non-zero static error constant. Okay, so firstly, the static error constant is determined by um, uh, first determine the type of the system. Okay, so this system is type 0 because S here in front of this denominator is power of 0. So it's a type 0 system. So for a type 0 system, I think you have steady state error when you use KP, or when you use unit step input. Okay. So I actually forgot the formula. So let's open up the slide related to steady state error. Okay, so for a type 0 system, the static error constant is Kp. So to determine Kp, you use this formula here. Limit of Gs when S approaching 0. So Kp is limit of S approaching 0 for Gs. So it's equal 1 over 2 times 3 times 7, which is equals 1 over 42. Okay, so this is the non-zero static error constant. And then you want the system, you want to design the system by having a static error constant equals 4. Or you want Kp equals 4, Kp new. So for lag compensator, again, we can look at the slide. So Kp new, now it's 4. Then we can determine the ratio Zc over Pc. So Zc over Pc equals 4 over 1 over 42. So it should be 168. So you have to define or determine the lag compensator that has ratio Zc over Pc equals 168. Okay, so let's do this on MATLAB. Okay, so firstly, we need to write the transfer function for this in MATLAB. Okay, so you have gain equals 1, and then 0 equals no 0, and then poles equals -2, -3, and -7. So later when you do the project part 4, you can refer the link that I included in the description of the project. Okay, so here I only show you regarding this tutorial. Okay. And then you can determine the transfer function for this system using ZPK. And then open up CISO tool. Okay, so this is the root locus of the system. And this is the step response or the time response at this purple point here. So when you drag this purple point, then the time response on the left or on the right will also change. Okay. Okay, let's go back to the question. So the question wants you to determine the system, the lag compensator at static error constant 4 and at 10% overshoot. So you can add the 10% overshoot by right clicking the window and choose the design requirements here and then choose new. And then in the selection, you can choose percent overshoot. So you want the percent overshoot to be 10%. So this black line will come out. So what you need to do next is to drag the purple point to intersect on the black line. Okay, so if you look at the time response on the right, then you will see that this is the system response at this particular overshoot. Okay, you can right click on this figure here. And then plot the characteristics. So for example, if you want to plot the peak response, so this is the maximum point or the point of overshoot, which is here is about 9.75, not really 10% because the intersection point here, maybe if you zoom, you can see that the point is not really intersect on this black line. Okay, so if you want to do it more accurately, you can just zoom until you get the point to be intersected correctly. So here now the overshoot is about 9%. And then you can plot the other things like settling time and also steady state error, the steady state value. So the final value is 0.493. And this is the settling time. Okay, so let's look at the question again. So you want to design a compensator that has static error constant of 4. So now you have calculated just now the ZC and PC. So for lag compensator, ZC must be smaller than PC. So we choose PC to be as close as possible to 0. let's say PC you choose 0.01. So ZC will be about 1.68. Okay, so we add this PC and ZC on the root locus. So first you add a real pole. Let's say somewhere here. Okay, because I never used this library before, so I don't know much about the library, but I will show you the example anyway. So then you can add the zero. So here the pole you add is about 0.164. So I think you can adjust the value later, but at this moment I don't know how to do it. Okay, so here if you add pole equals 0.164, then the pole will be about 27. So you should add it here. Okay, and then what you need to do is you just you can just move this point, the purple color point, so that it intersect the black line here. Okay, so when it intersect this black line, then you can determine the gain by looking at this loop transfer C here. So the new compensator will have this transfer function 1.1439 as the gain plus 0. The 0 is negative, which is 0.1641. Okay, so you can adjust this later in your project part 4, so that it intersect the black line here and then get the transfer function on this section here. Okay. The problem with lag compensator is that you cannot perform manual calculation because the calculation involves some tedious calculation. So for lead compensator, the calculation is slightly simpler. So let's look at an example for lead compensator. Okay. Example or tutorial question number 3. So in this question, design a lead compensator that has 20% overshoot with settling time reduction of 5 times. Okay, so the problem with this question is that it doesn't give you the dominant pole, okay? But in exam, you are given the dominant pole. So if you are not given the dominant pole, you can determine the dominant pole using MATLAB. So let's go back to MATLAB and determine the dominant pole. So firstly, the gain is equals to the zeros is there is no zero, and the poles are 0, minus 20, and minus 40. Then you can plot the root locus. Okay, so the system requirement is 20% overshoot. So you can add 20% overshoot on the root locus. So choose overshoot and change to 20%. So this is the black line for the percent overshoot. So just drag the purple or the pink colored point to intersect on this black line. Okay, so when intersected, you can determine the poles of this purple color location, the point here. So if you press the purple color point or the pink color, you can see at the bottom the location of the point, which is negative 6.19 plus 13.1 J, and the damping ratio and also the natural frequency. And I think you can look at the okay, you can only look at the point here on this section here. So this is the dominant pole. So let's write it out. Okay, so this is the dominant pole. Then you can determine the other things like damping ratio and also omega n. Okay, since you are given in MATLAB, you can determine straight away from MATLAB. So if you are not given MATLAB, let's say you are given this dominant pole value. So to determine damping ratio, you need to use the percent overshoot formula, which is this one in the slide. Okay, you have to use this formula to determine the damping ratio using 20% overshoot. Okay, so determine the damping ratio using 20% overshoot. So from MATLAB, it's 0.427. Okay, so if you are not if you are given the dominant pole, you have to determine the damping ratio using MATLAB, using the formula. Okay. So please provide calculation, but this one I don't calculate because I have MATLAB. Okay. But in exam, please calculate using the formula. And then to determine omega n, you can determine damping ratio times omega n equals this value here. So omega n will be Okay, so if you look at MATLAB, it will be slightly different. It's about the same, 14.5. Okay. And then the question wants to reduce the settling time by 5 times. So firstly, you need to determine the settling time for the system without compensator. So TS equals 4 over the damping ratio times omega n. So it's about 0.6462. So you want to reduce this by 5 times. So the new settling time will be 1 over 5 of TS. So this is the new settling time. So when you get the new settling time, you need to determine the new omega n while maintaining the same percent overshoot. So the new omega n equals okay, so the new omega n is 72.51, okay, which is the frequency is quite high. Okay, so after you determine the new damping ratio or the new frequency, then you need to determine the new dominant pole. Okay, using the formula negative damping ratio omega n nu plus or you can just determine from MATLAB. Okay, but in exam you have to calculate. Okay, but because I just want to show you the example. So itulah dia. Okay, so you need to determine this location here. Tapi malangnya tak boleh nak gerakkan point ni. You cannot move this point to this location because it's not on the root locus. So in the end, you have to determine the poles and zeros. I mean the dominant poles manually. Okay. So let's determine. Okay, so the new dominant pole is quite large. Okay, but anyway, then from here you can sketch them on an S-plane. Sketch all of the poles. And then choose a suitable value of PC and ZC. So for lead compensator, ZC will be bigger than PC. So you choose a value of PC. Let's say PC is somewhere here. Let's say you choose PC equals -5. Then you can determine ZC from the angle equals 180 degree. Oh, sorry, PC should be bigger. So PC somewhere here. Let's say PC. So let's say you choose PC equals -60. Then ZC should be somewhere located here. So let's determine this using MATLAB. So I will show you an example for manual calculation maybe next week. Okay. So in MATLAB, you can add a real pole. Let's say somewhere here. And then you can another 0. Let's say here. So you can adjust the newly added pole until the root locus intersect this black line here. Okay, dia sedikit susah nak intersect sebab dia terlalu besar. Okay. So later when you do the project, you will find similar difficulty lah. Okay. When you want to drag the pole, you will realize that your pole value is too big sampai tak boleh nak intersect. But you can keep trying lah. Okay. Okay, tak boleh gerak. Okay, tak boleh. Alright, so so that's it. So later on, you can try your project part 4. Okay, so project part 4 is due next week, Wednesday. So you can try and explore this functionality in MATLAB regarding the plotting of root locus and designing compensator. Okay, dia mungkin sedikit memenatkan, tapi it's actually seronok je sebenarnya. Okay. Okay, so that's it for today's lecture. And next week on Monday, I will show you one example of calculating the lead compensator, zero and pole. And we will continue with the last lecture 5B and tutorial 5B. Okay, so that's it for today's class. If you have any question, just text me anytime. Okay. Thank you very much. Assalamualaikum.
Waalaikumsalam, Dato'.